Hey guys, how you doing? Just wanted to finish 5.3 and then we'll look at the workbook right here. Just want to remind you that remember probability of at least one is going to equal the complement of probability of none. So the probability of none complement equals the probability of at least one. And if you want to think about this like logically, let's say we had a total of 7 trials right here. So the probability of getting at least one trial, that means 1 or 2 or 3 or 4 or 5 or 6, etc. Right here, the complement of that would be getting none. That is 0 right there. Okay, so that's why right here I have listed the probability of at least one equals 1 minus the probability of none. So let's take a look right here given this particular example. All right, so many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, use of rapid tests increased the percentage of clients who learned their test results from 69% to over 99%. The trade-off for fast results is that rapid tests are less accurate than slower laboratory tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of producing a false positive. False positive means falsely indicated that antibodies are present. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what's the probability that at least one false positive will occur? Assume that test results for different individuals are independent. So this is the multiplication rule of independent events right here. All right, so we figured out, first of all, from this information, the probability of a false positive is 0.004. And I figured out, I know I'm going to have to, I'll tell you why later, but I need the complement of this, which is that there's no false positives at all. There are no false positives. So that's 1 minus 0.004, which is 0.996. Okay, and that's why it's 0.996 there. So what are we trying to find out? We have 200 randomly selected people, right? And who are free of HIV antibodies. We want to know what's the probability at least one false positive will occur of these 200 people. All right, so we just found out, remember, at least one. We're going to say 1 minus the probability that no false positives occur of these 200 people. All right, well, we just said for one single person, it is 0.996, right? Well, sadly, we have a lot more than just one single person. We have 200 people, right? So we're going to say 1 minus 0.996. And this is where the general multiplication rule comes about. For one person, it's 0.996, but we have 200 people to the 200th power. Okay, so we go and calculate that. We have right there 1 minus 0.996 to the 200th power is 0.551. So there is my probability right there. The probability of having at least one false positive of 200 randomly selected people free of HIV antibodies is 0.551. Okay? There we go right there. So you can just also look right there. There we go. Okay. And there it is right there. That's the same way they've just first found out 0.996 times 200. They took that answer, subtracted 1 for it. Same thing. Okay. All right. Let's go on to the workbook stuff right now. All right. So this is page 97. Just remember that symbol right there means given that. And if it says right here, the probability of the card, if the whole statement right here, the probability of that the card is an ace, given that it is a red card, we say P of ace given that it's a red card. And we know conditional probability right here. Remember, the probability of A given B equals the probability of A right here. Or we can do the backwards, the probability of B given A equals the probability of B. So what we're trying to say right here is that if it's independent, that means that this B right here has no effect on the probability. Given that this thing happened, this B happened, it doesn't make a difference. They're still equal. All right, and like I said at first, you can also show that, probability of A given B equals A given B complement, but in my opinion, it's just easier to show it this way right here. All right, so let's look at an example. All right, is there a relationship between gender and candy preference? Suppose 200 high school students were asked to complete a survey about their favorite candies. The table shows the gender of each student and their favorite candy. Define A to be the event that a randomly selected student is a male. B to the event that a randomly selected student likes Skittles. Are the events A and B independent? Does the fact that, so what they're saying, justify your answer, they're saying, does the fact that a student, randomly selected student, likes Skittles, does that change the probability that a randomly selected student is a male? If you're just talking simply about students who, in general, just like Skittles, does that increase the probability that it's a male? Do a lot more males like Skittles, basically, is what they're saying? Okay, so we're going to go probability of A equals probability of A given B. So A is male, and right here, B is like Skittles right here. Okay, so probability of male given that the student likes Skittles. So the probability of a student being male right there is 120 over 200 right there. Okay, that reduces to 3/5, which is 0.60. The probability right here that the student is, let's go and just work this so you can see how I got this right here, that a student is a male given that they like Skittles. All right, let's see if we can figure this out. That means right here the probability of male and like Skittles over the probability, remember, you divided by just the second one is the probability that the student likes Skittles. Okay, now when we have a chart, this is always easier. So male and Skittles. So there's Skittles, that's in a row. The male's right there is 80, so that's going to be 80 on top. And then right here, the probability just over the probability just that they happen to like Skittles. So we can just say 80 over the total right there of Skittles, which is 140. We don't have to do the whole 80 over 200 divided by 140 over 200 because 200 just cancel out. So we can just say 80 over 140. All right, so 80 over 140 ends up giving us right here 0.571. So they are not equal. That means that the two events A and events B, are not independent. All right, and since we showed work, that should be enough right here. But if we have to do some type of explanation, we can just say, knowing that a student likes Skittles actually changes the probability that a randomly selected student is a male. You don't have to write this right here, but if something asked you to justify it anymore, you would write right here, knowing that a student likes Skittles changes the probability that the randomly selected student is a male. Now, to get a 4 right here, all you have to do, though, is to show your work and just show that the two probabilities are not equal. That's good enough. The explanation might be more for some type of longer open-ended that just asks you to analyze it more. On this particular problem, though, just showing the probabilities is good enough that they're not equal. All right, let's look at now, right here, we're going to do we are going to end up doing right now a tree diagram. All right, we're going to look at a tree diagram right here. Okay, let's take a look. A study of high school juniors in 3 districts, Lakeville, Sheboygan, and Omaha, was conducted to determine enrollment trends in AP Mathematics courses, calculus, and statistics. All right, so let's look right here. I'm just going to highlight 42% of the students in the study came from Lakeville, 37% came from Sheboygan, and the rest came from Omaha. In Lakeville, 64% of the students took statistics, while the rest took calculus. 58% of the juniors in Sheboygan and 49% of the juniors in Omaha took statistics, while the rest took calculus in each district. No juniors took both statistics and calculus at the same time. Describe a situation using a tree diagram and find the probability that a randomly selected student in the study took statistics. Okay, so remember what you're doing. We did this today. First, we're just going to do the general, and then we're going to do the conditional. And, we'll keep on. There could be more than just one, but in this case, we're just going to do the general and conditional, and I think that's it. Let's take a look here. So the general right here is, first we have a randomly selected student. All right, so we have 3 different districts right here. We had, first of all, Lakeville, and then the next one we have is Sheboygan, and the final one we had right here is Omaha. All right, and then we're just going to write each of the probabilities that we have right here. So the first one right here is 42% of the students in the study came from Lakeville. 37% came from Sheboygan, 0.37. And the rest came from Omaha, so we just have to add 42 plus 37 is going to be 79. So 1 minus 0.79 is, of course, going to be right there, 0.21. All right, cool. Next, right here, let's go and do the conditional part right here. In Lakeville, 60% of juniors took statistics, the rest took calculus. So we have right here, from Lakeville, right here we have 64% of juniors took statistics. So we're going to say 0.64, and they took statistics. Now the rest right here took calculus right here. So we say 1 minus 0.64, which is going to give us right here 0.36. So 0.36 took calculus. Now, if you want to, just to make your life easier, I know that's going to be all the rest of them, statistics and calculus. And I'll do that for the third one as well, just to make life easier. So no problem. So let's look at Sheboygan right now. So we did Lakeville already. In Sheboygan, we had 58% of juniors in Sheboygan took statistics right here. So to get this right here, we say 1 minus 0.58, which is 0.42, took calculus, because they said the rest took calculus, right? And for the final one is Omaha, right? So for Omaha, it looks like 49% of the juniors in Omaha took statistics. 0.49. And of course, 1 minus 0.49 is just going to be 0.51 right here. Okay? All right, so let's get rid of that right there. All right, so we got it right there. Describe the situation using a T-tree diagram we just did, and find the probability that a randomly selected student in the study took statistics. So probability that any randomly selected student in the studies took statistics. All right, so we have to figure that out. Let's get this right here. So we want that one, and that one. So to get those probabilities, there we go. There's the second one, and there's a third one, and we have to multiply right here, right? So we're going to say right here, first one is going to be 0.42 times 0.64. Then we're going to add to that, right? Because it could be Lakeville in statistics, or Sheboygan and statistics, or it could be Omaha and statistics, right? So Lakeville statistics, or Sheboygan statistics, or Omaha statistics. So that's why we're multiplying, then adding. So the other one is 0.37 times 0.58. And then finally we have 0.21 times 0.49. All right, so let's go ahead and calculate this all right here. And you can do this all at once if you want. So go ahead and say right here, 0.42 times 0.64. Then we're going to add to that 0.37 times 0.58. Then we'll add to that 0.21 times 0.49. Okay, we get 0.5863. No problem. 0.5863. Just double check that there's no mistakes right here if you want to. But I think, yeah, we're all good right there. All right, I usually have to double check because it's a computer calculator, but it looks actually pretty good right here. So 0.5863 is our answer right here. Is the probability that a randomly 0.5863 is the probability that a randomly selected student is taking statistics. Okay, there we go. Now this right here is the next one, is calculating conditional probabilities. I already talked about this. All right, so the probability of B given A, or the other way around, A given B, it doesn't matter, is going to be, remember, the probability of A and B divided by the probability of B. So most conditional probabilities can be determined using a two-way table, Venn diagram, or tree diagram. However, the formula can also be used if you know the appropriate probabilities in the situation. Now right here, they said to use a tree diagram, the same situation we already did. But now they ask a question. Find the probability that the student is from Lakeville, given that the student took statistics. All right, so if we figure that from a formula, that's going to be probability of, I'm going to put L for Lakeville and S for statistics, Lakeville and statistics, divided by the probability that they took statistics. Now, we already got the probability that they took statistics. It is right here. That is 0.5863, so let's enter that in. The probability that they went to Lakeville and took statistics, let's look at that. Lakeville and statistics, that's right here. And this right here is going to be 0.42 times 0.64. So that individually, 0.42 times 0.64, ends up being 0.2688. You can round that to 0.269 if you so wish. But actually, if you're doing the problem, just keep the raw data now that I think about it. So 0.2688 is good. And then round once you finish it. So we're going to go and divide that. So 0.2688 divided by 0.5863 is 0.4584 is our answer. Now we can round if we want. All right, so if you want to just round that to 0.45 8, that's fine, but I'll keep it as 0.4584 actually. So there we go. The probability the student is from Lakeville, given that they took statistics, is 0.4584. All right, that is it. Have a good day, guys.